This video is going to be an example of investigating a function by making a bunch of plots. So the function that we're going to be interested in is called Bessel function. So we're going to import NumPy and pyplot in the usual way, but we're also going to import this library called SciPy, which contains the definition of the Bessel function. So we're just going to call it J2x. As the usual notation for this function is J subscript 2, so we're going to call it J2x. In the SciPy library, it's have to do it like this: scipy.special.jv of 2, x. Okay, so let's just have a make a plot size 10 by 5. We're going to run from -50 to 50. 1001 points, let's say. So we're going to do plot the y's against the x's, and here I've just put in this argument little r. That's equivalent. That's a standard abbreviation you're allowed to do instead of color equals red. So there we go. We'll just move the x-axis up to the y equals 0, just to make it a bit clearer. So let's just remember the normal way to do that. We're looking at the bottom spine. That refers to this line that's across the bottom at the moment. And we're going to do the set position method. And I'm going to move it to the 0 position, which means in the middle of the plot. Okay, so we see we've got this kind of oscillation, but the oscillations are sort of gradually dying down as we go to the left or the right, and you can see that it's actually an even function. The same value at -x as the value at x. Okay, so one thing we can do is to just try and investigate what it looks like in the case where x is small. So let's do a similar thing here. But instead of plotting from -50 to 50, let's just do it from just a small interval near the middle. Not quite sure why is it. Okay, so we need to do the fig ax thing again here. Make a new plot that we can plot stuff on. Okay, so there we go. So here we are. We've got the plot of the Bessel function, and it looks like a parabola. So maybe let's just compare it with a parabola. So let's maybe plot that in green so that you can tell the difference. Okay, so we can see that the green curve is quite a bit bigger than the red one, so it's not quite right. So let's just maybe multiply it by 0.1. Okay, we multiply by 0.1, then we find that the green curve is sort of kind of looking very similar, but not quite the same. Actually, so what we can do is let's take out that plot here, and then let's divide by the y's. Okay, so we've got a bit of a problem here that we've got a y is equal to 0 in the middle. Okay, so actually one way we could avoid that is let's just change this here to 1000. Okay, so if we do 1000 points, then 0 is not going to be one of them. Okay, so for some reason we've got this huge vertical extent. I'm not quite sure exactly why we've got this huge vertical extent here, but we can see anyway that the ratio is around 0.8. So that suggests if we made it 0.125 here instead, then the ratio would be close to 1. So let's just go back to here. So we'll plot the y, and we'll also plot 0.125 times the x is squared. Okay, now we can see that these things are matching up very closely, and we notice that 0.125 is 1/8. So let's tidy this up. Yeah. Okay. So that's kind of our first estimate of what's going on close to the middle, close to your 0 here. The Bessel function is looking very close to x squared over 8. Okay, another thing we can see is, we can actually, let's maybe shift this over here, go back to here, and then instead of 0 to 50, I mean, there's no point really plotting the negative values, because you can see that it's an even function, so the left is just the same as the right. Let's instead just plot out the positive values, and you can see these oscillations are kind of dying away rather slowly. So let's maybe just try and work out the rate at which these things are dying away. Okay, so let's actually we'll go back and use this plot again, and and again, so let's to avoid difficulties when x is 0, let's actually change this thing here. So we'll go from 1 to 100, say. Okay, so there we've done the Bessel function, we've done 1 over x. Okay. But you can see that the 1 over x is kind of dying away much faster. So, that's kind of not really capturing the behavior. So what we could do instead of 1 over x is we could do 1 over the square root of x, or like so. Now you can see that this kind of seems to match up rather better. And actually, let's make it. Let's start a bit further out to the right. Let's maybe start at 5. Okay, so that's so this is kind of definitely the right sort of shape, but not quite the kind of constant. Let's multiply it by 0.9 and see what that does. So it's still too big. We do 0.8. Okay, 0.8 looks very good, right? So 0.8 is sort of matching up the tops, and if we did 0.7, then that's clearly sort of too small. So so it's looking pretty much like the asymptotics of it. It's going like a 0.8 times x to the minus a half. And let's also plot the kind of negative version of that. maybe we can do that in blue. Okay, so again, yeah, so we can see that we've got an oscillation between this upper envelope of 0.8 x to the minus half and the lower envelope of minus 0.8 x to the minus half. Okay, so let's kind of try and understand what the oscillation looks like. Okay, so for that, well, let's make a new another new plot. Okay, so there's we're going to put our Bessel function. Let's divide by this envelope that we thought that we had. So that was okay. So this is looking very much like a sine function. Actually, let's maybe make it not plot quite so large a range. We play just say 50, and then we can kind of see it. Okay, so let's do that, and then okay. Oh. Okay, so now we've plotted the sine function in green, and you can see that it matches up quite nicely, but it seems to be shifted by a bit. Okay, so so we try and shift. We try and shift our sine function here. We shifted it by pi over 2, which is like 1.5. So that seems to be too much. Okay, so we shift by 0.1 pi. 0.2 pi. Okay, that seems to be doesn't seem to be okay. If we do 0.25 pi, then it seems to be kind of pretty much in antiphase. Okay, so so we do kind of 1.25 pi. You shift by pi, that will change the sign. Okay, so now you can see that if you shift by 1.25 pi, then the oscillations kind of seem to match up. Okay, so so kind of putting this together, we can see that. Let's make a new plot again. Now we're going to plot the Bessel function, and so what have we learnt? We learnt that the envelope is like 0.8 and then the oscillation is like so. Okay. So now here's the Bessel function. Actually, let's that was in red, and let's just be explicit about that. Let's put this one in green. Okay, so now the green curve and the red curve match up pretty closely. So we found that this is a pretty good approximation to the Bessel function. 0.8 x to the minus half times sine x plus a quarter pi plus 1 1/4 pi. That's as x gets reasonably large, this seems to be a very close approximation. And you can see that there's some kind of divergence when x is small. And so then that will be the end of our kind of graphical investigation of the behavior of the Bessel function.